Um, so hi, this is Matthew Hansen. I'm discussing Project 3, generating the Hamming code for 7.4, the 7.4 Hamming code with a distance of 3. I'll go into each bit of the code. We'll do sequential first, and then threaded. You'll see they are very similar thanks to one of the main concepts and annotations within Julia language. We'll talk about some of the differences between the performance between the two. So let's get into it now. You'll see I'm starting down this far because this is actually where the main function starts. This really probably should be in a main function, but everything above this line is encapsulated within its own function, so this is kind of just the main logic that we're running through. Julia would probably have some slight performance improvements if I had put this in a main function, but not by much. Anyways, so here's the actual bits, so I'm going to change this back. So when we're looking for a Hamming 7.4 code, the 7 is the number of bits that we're looking for, 4 is the length of the actual data that we're passing, and if you do the calculation, we'll end up with 3 as the distance of parity bits that are required in order to make corrections. So you can have a data length of 4 when you start off with 7 bits. So in here you can see I've actually, the n, k, and d values are in fact labeled. Julia has this cool concept where you can create a list using the collect, using this slicing operator where we're going from 2 to the number of bits, which is in this case is 7. This would normally be 128, but because we're starting at 0, we need to go to 127 bits. So this is from 0 to 127 in integers. And then we're going to go ahead and cast each one of these integers into a binary number. So let me go up to the function int to make bit string. This is very Julia specific, so probably not that interesting. But what happens is we are creating, well, we're taking the integer that's passed in, we are padding it, the number of bits that it needs to be, and converting it to a binary number. And then at the end, we're converting it into a string. However, this is actually a char array. So at the end, we combine them all, even though this looks like a multiplication operator. And Julia, this is how you concatenate strings. So we're concatenating the chars into one giant string. And although you don't see a return here, you will see it in other places. In Julia, the last line of a function is what is returned, unless specified differently. So that's actually what's doing the conversion from integer to binary. Not very important for Hamming code, but just a fun little detail there. So the first thing I'm doing is I'm popping the 0 out because we know we're starting with 0. So I'm grabbing the first of the binary numbers, which we know is 0. I don't have to do this. And then I'm separating out the non-zeros by slicing from not 0 to the end of the list. On this line, specifically what I'm doing is I'm filtering all of the elements that all of the integers that are left in the list, so it's just 0 that's been popped out. I'm trying to make sure anything that's left in this list has a Hamming distance of at least a 3 in this case, and I specified the distance here. But this can be changed if you want to change things on the fly. And it'll still work fine. So the actual Hamming distance, so there's actually 2 functions that it's calling. So you're passing in the comparer, which in this case is 0, and the comparee, which is whatever element it's being compared to as it's iterating over the list, and the minimum distance that it needs to be. And so what this function returns is the generated Hamming distance between the comparer and the comparee, and making sure that that is in fact greater than or equal to the minimum distance, which is in this case 3. So here you'll see this is very, very simple. It's just a for loop over the length of the 2 strings and making sure that at each index they're the same. If they're not the same, then it increases by 1. So for example, if you have like 001 and 000, well, the last index would be different. And since they're different, then you know your Hamming distance is at least a 1 because of that last one, although it would have been the same for the other 2, so this wouldn't have been corrected in that case. So really simple way of doing it, not the most efficient. A binary, well, using XOR is much more efficient. but Julia is weird in that it doesn't have a native bit type. There's some a little bit of weirdness going there. And performance-wise, either way, you would really have a for loop, whether you're doing an XOR or not, because you still need to count the number of ones. So this isn't actually necessarily that much worse, even though strings are normally pretty bad. But it's at least it's not a command that's in the CPU normally, so it would be a little bit worse. So this filtered non-zeros is what happens once you have all of the integers from 1 to 127 minus the ones where the Hamming distance is less than 3. If it's at least a 3, it's in this list. So from here, this is really the main logic of the function. I put a results dictionary together so I can keep what bit string I'm comparing, which is the comparer, and going through each item in this list exhaustively, because it's going to do this calculation for every single one. And it goes ahead and it runs this function. I'm going to get to this function in a bit because that's where the main logic takes place. But what it takes is the comparer that we're looking at, so the bit string in this case, all of the filtered non-zeros, an aggregate. Now this is a list right now with just the bit string of 0 in it, because you know that 0 has to be in it. And then we're taking in the distance that we're trying to compare with. So in this case, it would be the 3. Here is a line I included in case you want to see each of the generated numbers, so we'll go ahead and comment that so we can see that. And then here at the end, once it's generated, this is the bulk of the work, once it's generated all of the Hamming codes for those that are at least a distance of 3 away from 0, then we're going to go through and we're going to see, okay, well, which one's the largest? And we're going to do a double check here just to make sure it's valid. This check is kind of unnecessary, but it was a nice peace of mind step for me, at least to make sure that all the elements are actually valid. And so at the end of this, we'll have the largest list, which we know will be at least 16. And then we'll go ahead and print that. So here you can see the weird string concatenation in effect in Julia. So I'm going to go ahead and run this. So to run it, you just run Julia, because this is an interpreted language, so you're going to run the program Julia and then the name of the file. So in this case, we're running sequential.julia. So you'll see that was very quick. We'll go into the speeds in a little bit. But you'll see for each one of these codes, and there's, I think, 99 bit strings that were a distance of at least 3 from 0. For each one of these, it goes ahead and checks. It prints whether the list itself is valid or not. And then here it'll print the length of the list, and then here's the list itself. And so I manually verified quite a few of these lists, and they seem valid to me. So you'll see all of them start with 0, because of course 0 is going to be in it. And then the first element you'll find for all of these lists will be the bit string it's comparing, because of how the algorithm that actually calculates them works. Which I'll go back into actually. But before I do that, at the end you'll see here, it'll print the list of Hamming codes that's the largest. So in this case 16, you'll notice that there's actually several 16s, because there are several possibilities that are valid. So let me go back to the code. Let me explain the main part of the logic here. So as it's going through and comparing each bit string and generating the list of Hamming codes, what that looks like is this list, this function here. So the easiest way to do this, at least for me, and I think the cleanest way of doing this is recursively, although recursion does have a performance hit, because you're actually referencing pointers to functions instead of just manually manipulating the data. But anyways, it was fast enough for me, and as you'll see in the threaded one, each one of these comparers is run on a separate thread, or at least up to the max number of threads that I have. So it's still not a huge hit, even though from there it runs sequentially. So the first step in the recursion is to add the comparer to the aggregate. So on the first run, we know that this was just the 0-bit string. Well, we already know from a previous filtering that, of course, this is going to be valid, so we're going to show that in there. As long as this function is running, the compare will be valid, so whatever the list is. So we're going to add that in there, and as it moves forward, the aggregate list will grow, and then at the end, that's what we're going to return, because the aggregate is the list of Hamming codes. The next thing we're going to do is a little bit complicated, but what we're going to do is we're going to remove the compare from the list that we're checking, and this list that we're checking is what shrinks every single time. So we remove that, and anything that has a Hamming distance that is, well, in this case 3, but anything that has a Hamming distance that is smaller than 3 from the compare. So this way we're actually filtering out, we're making the list smaller each time we go by saying, okay, well, if it's less than 3 from our compare, get rid of it. And so at the end of the time, at the end of the recursion, we have our exit condition, which is if there's nothing in this filtered list, then we return the aggregate. We've already filled it up. Otherwise, what we're going to do is we're going to call this function again. And now that we've popped out the compare here in this part of the filter, the first element in the list, and Julia is 1 index, so it looks a little weird, but whatever the next item in this list is the next compare. And we're taking what our original list was, since it was filtered, it's this new shorter list, as well as the aggregate that should just have the compare from the last run added and the distance, which is unchanging. So as this runs, it will add whatever the compare is, shrink the list down, and continue that process until there's nothing left in that list to compare. So, yeah. Other parts of the code left is this valid function, which isn't as interesting. It's mainly just doing the same thing over again. And making sure that all of them have a Hamming distance that's at least 3 away from the compare, which is in this case 0. So, but it checks each item in the list, as you see here. So that is interesting. And then the display is what you saw earlier. It's just some formatting stuff to make it a little bit more concise, as well as our final print statement just showing the results. So next up is threaded. Now we don't actually have to go over much of it because Julia is actually kind of nice. So you'll notice everything in here and up above is the same, minus some of the display logic, which I'll get into. And I'll uncomment here as well. So the main difference is where before we were just calling, in our main for loop, we were calling this recursive function and setting it into the dictionary. We're still doing that here, but the big difference is between here and here is this is just a normal for loop, whereas in Julia you can use a threads annotation. And what this allows you to do is pass in command line parameters that specifies how many threads to run the for loop on. C# is a similar concept with the parallel for loop. So anyways, having done that, each loop of this for loop is going to go ahead and run on a separate thread as is available. To prove that, there's some command. I have this pretty print statement that will show what is actually the bit string being compared, what thread it's running on, and what the list looks like at that iteration. Or actually as the result of the final iteration. So let me go ahead and run this. So to run this in Julia, all you have to do is run Julia with the -- threads command, and then you can specify the number of threads. So in this case, I'll do 16, and then the name of the Julia file. So if I run that, you will see we have 16 threads having total run, and you'll see the thread number changes per loop, although 16 isn't the most efficient. You'll see what the bit string is that's being compared, as well as the list that was generated for it. I forgot to change this back from a previous test, so I'll go ahead and change this back to a 7 and rerun that. So we'll see 16 is in fact the correct amount. And this is a valid HammingCode, a list of HammingCodes. So that is how you run both the sequential and threaded version. There is no difference in logic between the two because I'm still using the recursive algorithm or the recursive function on both. It's just the for loop that where I get the benefit, at least on bigger data sets, of multi-threading. So to prove that, I'm going to go ahead and run the measure command tool, which is like time in Linux. And as you will see, what it does is it'll print how long it takes for a program to run. This is actually quite slow. When I did my averages earlier, I ran this command 10 times for both sequential and threaded. And for threaded, I did it with both 16 threads and with 8 threads. So anyways, it's not always stable, depending on what's going on. I think it's because I'm recording now that it's about 200 milliseconds slower, which is fine. It makes sense because some threads are being used up. Well, shouldn't necessarily get it, but that's probably what's happening. If I go ahead and run the command for the threaded algorithm, I'll do 16. This, as you see, took longer, although this was very close because of doing stuff at the moment. However, over the period of time, the averages turned out to be a little bit slower because of the overhead that's involved with sending the process to multiple threads. When I tested briefly earlier using 8 bits instead of 7 bits, the actual performance benefit from using multi-threading started to show. It wasn't dramatic, but I think as the number of bits increases, multi-threading becomes a massive advantage. Although Julia happens to be fast enough for sequential for 7.4 is not really an issue despite the usage of actual strings. So yeah, that is my implementation of Project 3, generating the 7.4 HammingCode with a distance of 3 for the number of parity bits. Thank you.